Dude, hello, hello, hello. All right. Oh, all right. Hello, hello, hello. All right. We got a Lila. We got a Mancha. We've got a Raymond. We've got a Tania in 2D. We've got a hello. We got a Nico. We got a Michael with the kid. All right. With the mini. We got a Luis. We got a lot of chat. We got Montserrat. I said Nico, we got Louis, we got Tiny. Oh, Tiny are both in the chat and the 2D thing. And you notice there's now a portal for the 2D animated blah blah blahs. Oh, Montserrat. What's going on there? Whoa. Okay. It's like almost a Pokemon, but not. And Harris. Okay, good. Anyway, good. Thank you. Appreciate it. Good. Yes. Hope you could good. Thank you. Thank you, Harris. Thank you, Tania. Thank you, Jerry. Who else did I? Yes. Okay. Feeling good. Thank you. I mean, it's day by day. But thank you. Um, okay. Uh, oh, Joyce. Hello, Joyce. Okay. Excellent. Oh, where'd the board go? Wait a minute. Hello, hello. Is it there? Yes. Okay. Okay. So a couple of quick things. I always say that, and I'm always lying. I want to get back into some physics here. I kind of like physics. Um, So last class, okay, so a couple of things. Last class, I kind of got bogged down, sort of, alerting you to the dynamics of an exam in my class. Okay, so we talked about that. So yes, now we are moving toward an exam. But again, of course, in your class, it's not posted. It won't even be posted till a week from this Thursday, right? If I'm right. And then it'll be due the following Monday. So we've got a number of classes before then to both continue with the material and answer questions about the practice exam, et cetera, et cetera. In other words, today I want to get back to material. Just remember at any time, especially if you've never had me before as a professor, which is most of you or all of you, because you all took 203 like in the summer or in this anyway. The way to study for an exam for me, the way to prepare is to just live and breathe by the practice exam. It's like all about the practice, like skip straight to that. Don't use the practice exam to find out what you need to learn better and what you don't, et cetera, et cetera. And I will increasingly, like many of these classes, I will either explicitly address things in the practice exam as we get closer, or you'll raise questions in class in the next couple of classes about things in the practice exam. And of course, you can find old videos with solutions to just about and walkthroughs to just about everything in the practice exam. So it is all about the practice exam, right? Um, however, no, however, I mean, that's the case. Um, but I do reserve the right and the ability to update the practice exam as we get closer. Wait, let me put this a different way. Nothing that you will not have anything on your exam that doesn't at some point appear in the practice exam. Like it's not meant to be a trick. If you know everything cold in the practice exam, you should be set for the actual exam. That is the case. However, I do reserve the right to update the practice exam, and I'll warn you if I'm going to. Partly because I find errors in the practice exam as we get closer, or things that can be clarified better or whatever. But also, I reserve the right to update it so it most directly reflects however things are happening in this particular class, in your class. Why I'm saying all of that is it is possible between now and 2 weeks from now that I might take some things away, but more particularly, I might add something to the practice exam that, as long as I add it in time, like before your exam, would make it fair game for your exam. And why would I say that? So again, let me say this slower. There won't be anything on your exam that isn't somehow represented in the practice exam. And any or every update I ever do to the practice exam is a sign to you that I'm trying to make it more realistically resemble your actual exam. It's not to trick you. So because your exam is a little bit late in the semester, or like later than it sometimes is, and because you actually are really doing well progressing through the material, it is possible that you may be responsible for there may be a wave problem on your actual exam that does not appear in recent practice exams. And that's what we're going to sort of get to, in other words, something like related to lab 3, something related to the issues of lab 3. Um, so if that, so you won't be surprised or shocked if I update the practice exam. Take note of the update and take it seriously. That's what I'm trying to say. Okay, so that's that. So today we're going to do more about waves and the stuff that we would have started last time, but I got so bogged down talking about the exam. So wave equation and wave speed, and Doppler effect. Now, last thing about that, the last couple of homeworks have asked you to sort of really think way ahead of where I am in the lecture material or where I've been. And I'm aware of that. Like the last two homeworks. First, the Doppler effect. You had to do this Doppler effect homework way sort of excessively before we ever discussed it in class. We're now finally getting to the point where we can discuss it in class. I'm very aware that that was a big stretch. So as always, of course, you have plenty of time to revert once we get to this and unpack it in class. Of course, if you made any kind of valiant attempt when it was due, you absolutely can revise, re-upload, and get all the points. Okay. But I'm aware that it was a particular stretch for many of us. Similarly, the homework that was due today, that it was like almost like extra credit in the sense that like I even warned you in that homework that I'm not sure how much of that I can go over in class or will even be on your exam, but it's just like important material to be included in the curriculum. So just very quickly on that, that was a big stretch too. Like I haven't said anything about any of those concepts in lecture. You had to sort of find them out on your own. I'm very aware. So any of you who did that, especially if you did the whole thing, like you definitely got all of the points. If you did the whole thing and did all of it without any help from me at all, like Pork bless America, good for you. If you turned in anything on that homework at all, even if you're not finished yet, but if you turn anything in, you still can get all the points on it. Again, that one, so the tone, the one that was due today, is kind of a weird homework because it's out of nowhere and we're not really going to discuss it much. So definitely you can, if you are willing to make you're willing to stretch yourself to do that homework, you certainly, it's like bonus 40 points, whatever. But forgive me if we're not going to discuss it in depth in class. Doppler effect, the other one, we absolutely are. That's what we're getting toward in a few minutes or in this week. And the Doppler effect one absolutely always appears on an exam, whether it appears in the midterm or the final. I promise you, you have to know the Doppler effect, like at an exam worthy level. So even there too, you can still revise or re-upload or whatever for all the points once you learn more about it from me in lecture. All that being said, what I'm trying to say is I know the homeworks have been ahead of the game for you sort of disproportionately recently. Therefore, let me be clear, there's no new homework. I don't believe that I'm assigning any new homework between now and your exam. Everything you do now is for me to catch up with myself or catch up with the work you've done or catch up with the lab material. It's basically all the time from here to the exam is for me to sort of catch up with you and you to catch up with yourselves. If you're behind on homeworks or behind on understanding, we're all going to catch up with each other and try to put this all together for the exam in 2 weeks. And we have like 2 weeks to do it. So if it seemed a little, so basically you can breathe like nothing new in the way of assignments will be coming your way between now and the exam. So just focus on putting the material together, catching up where you are, trying to make sense out of it, and getting yourself ready for this exam. I.e., when in doubt, just go to the practice exam and just like do it without looking and do it over and over. Okay. I obviously I could say more about that, but so I'd like to get back to the material now. I'm gonna get back to the material and sort of pick up where I sort of left off last time and where you sort of were. I'm picking up on the concepts from lab 3, which I know is now a while ago. But lab 3 is super important, and it's classically super confusing to people while they're doing it. No one ever knows what, I mean, it's sort of fun, but no one ever really knows what's going on while they're doing lab 3, and certainly when they do all the analysis. Like, I'm aware of that. Now I'm going to try to make some sense of it. Maybe it had by lab 4, maybe it does make sense to a lot of you, but I'm going to try to make sense of it now. Sorry. So I'm looking in the chat. And then I'll get going. We love the chat. Wait, and who else did I not say hello to? Oh, hello, Jadith. Sorry. And who else did I not? And hello, Harris. Thank you for asking. I'm doing well. Thank you. And hello, other people that I didn't. Okay, but in the chat, quick question. How far back? Oh, yeah. No, great question. Nico and anybody else. No, as far as until I explicitly say otherwise, if a portal is still up, as long as the portal's up, like homework 1, you absolutely can still revise, fix, and upload, especially if you didn't get all the points and you got any kind of feedback from me anywhere that can use to, yes, all of you. Homework 1 is still fair. I mean, we haven't even had that many homeworks, right? So whatever. Homework 1B is still totally fair game. Homework 2, which is very long, and there's still parts of it we still haven't discussed. Anything is still fair game to revise and re-upload for the remaining points. Absolutely. I'll tell you when any curtain closes on any of that stuff. Number 2, let me say, it's a fair question. There's 2 more things about that. Number 2, like homework 1 and homework 2, well, I mean, all the homework, but really homework 1 and homework 2 are very worth knowing and practicing and making sure you're straight on before this midterm exam. So, I mean, again, if you're pressed for time and you're trying to directly study or prepare, I would go straight to the practice exam. I would. And it's not cheating or even if you still feel like you're fuzzy on things, figure out what you're fuzzy on by going to the practice exam. However, and yes, the exam is worth more points than any individual homework. So if you're making a choice, don't spend so much time revising old homeworks that you never get to practice for the exam. But if you go to the practice exam and try to study for the exam and stuff and prepare for it and see what the material is, many of you will find as you're studying or practicing, many of you will find that, especially, for example, like homework 2, it might have looked crazy and out of, just mathematically obscure to you at the time. But now that we practice a bunch, and once you're practicing directly for the exam, you can take a break or whatever, and you want varied exercises to see if you know what's going on. Then go back and look at your homework 2, and you'll be surprised that it serves as good practice, good exercises, and it may seem a lot easier to a lot of you now than it did when it was first assigned. So for sure, in the middle of studying, go back to practice it to homework 2, for example, or 1. And if you don't have a perfect score on them, you can do double duty by redoing it for practice and then resubmitting it, getting the points, and it'll help you for the exam. And that's sort of the point of the whole system. So yes, I'm sorry to dwell on it, but yes, I'm still accepting. I will continually be accepting revisions. The goal is for you you are entitled to get perfect scores on all the homeworks if you do them enough. That's fine by me. The only catch to all of this, the only catch is if on any homework, especially going back farther, 1 or 2, if you didn't hand in anything for it when it was originally due, then I will still accept things even this late, even homework 1, I will, but you won't get all the points is the only difference. If you never turned in anything for it, you still should, really, and you should still try, and you could still revise and upload to get a lot of points. But if you didn't turn in anything when it was originally due, then you're not in a position to get all the points. But it's still worth it. But the punishment is not big enough to not be worth it anyway. I hope that's clear. Wait, sorry. Oh, great. Thank you. Okay, thank you for the closing the loop, Nico, and good question. Okay. Okay. All right. I think. Oh, wait. No, there's something else in the chat. Sorry. Hold on. Oh. Wait, no, okay. This is a very good question in the chat. Hold on. I'm just afraid I'm going to rabbit hole. No, it's a very good question. Let me just think how I could say this concisely without rabbit holing myself. Okay. Okay, question in the direct chat. And of course, this person should submit for points now. Like, I'm not going to mention the name because it's direct chat, but it's a great question. So someone said in the direct chat, could I explain what WWW means? That is a comment that I sometimes make and particularly made on many people's Doppler effect homework. Okay. Why this is such a good question. It's a fair question, but it's also good in terms of the upcoming exam. So let me back up for a second. Right. In general, most of my 3-letter acronyms are like steps from the 5-step method. Like, yeah, part of what I'm trying to get people used to in general. Like, I hope people know the steps well enough to know at this point, like that at this point, if I just write down something, GDP, or 3 GDP question mark. I'm saying I don't see your step 3 general definitions and principles. And if it's like homework, well, whatever it is, I'm saying now, therefore I'm taking off points. Or like it's both a critique, a feedback, but it's also specifically like a grading rubric. This still doesn't answer the question, but just as a warning, again, one of the reasons that I'm so intense about the 5-step method is it is a built-in grading rubric. When you are writing out your exam to me, like ask yourself as you're going, do I have a step 1? Do I have a step 2? Do I have a step 3? And like label as you go, because if you can label every one of those steps, you're in effect doing a checklist for yourself of that you're getting all the points. Okay. So that's what most of those 3-letter acronyms are meant to be handy that way. Now, however, you're absolutely right. I have a couple of 3-letter acronyms that are not literally part of the step method that I never literally explicated to you. So one of them is WWW. This is to everybody. It's a very fair question. And yes, it came up on the Doppler effect, which we're going to start getting into. If I say WWW, what I'm saying is, what is this? Where is it from? Why is it true? Or something like that. It's like what, why, where from? Now, what that means when I write that, and this is particularly important on exams, if I write WWW, what I'm probably saying is what you just wrote is probably true. Like it looks like a legitimate physics equation. Like I know what this is that you're writing. But what I'm really saying is, hang on, that was out of left field. Like 9 times out of 10, if I say WWW, I'm saying something is true, but I don't think it's directly coming from class material. I don't think it's a step 3 GDP. Like I don't think it's a principle. I don't think it's a fundamental idea. I think it's some kind of derived equation that came from earlier equations that in fact that maybe people use in the world, but I'm not even sure that we use here. Therefore, it still might be true. But therefore, because it's a derived equation, first of all, you have to go to extra effort to derive it. Like you really have to justify whatever this thing is that I'm writing WWW. Like you really have to show why it makes sense stuff because really honestly, to tell you the truth, generally when I write WWW, it means it's some kind of equation that I know came from the web. And that doesn't mean you cheated. I'm not saying that someone cheated when I write WW. Like it doesn't mean you did something ethically wrong, really. But it does mean it's sort of a flag to me that you're pulling things like not from the class. And so you really have to be extra careful to tie that conclusion back to whatever the material is from the class. You have to show that you understand it. It's not good enough that it's true or that it works. So especially on an exam, it's a red, like you don't really want, I'm never going to like, I think you get my point. Once I write www, it means I'm sort of leaning in and paying even more attention to what's going on and like, where's all this coming from? And do you really know what you're writing? Or are you putting pieces? Now, again, that's not an accusation. Often people in very good faith, of course, are getting things from the web and stuff. But like, you got to understand what you're writing down. Now, specifically with the Doppler effect, I'm going to talk about this in detail when we unpack it, but there is a Doppler effect equation that's all over the web that people use all the time. Like, I'm not blaming anybody. I'm not shaming anybody. I know the equation that I probably wrote that about. There's an equation all over the web that's legitimate. It's like correct. Okay. But it's such a super shortcut that it totally does not help anybody understand anything. It's just like a formula. It's like a classic science where you just like plug and chug and you without really understanding what conceptually is going on. And B, more specifically, it's actually a hard formula to use correctly because again, I'm getting ahead of myself, but with the Doppler effect thing, there's this equation that a lot of people find on the web that is a fraction, and in the numerator there's like a plus or minus sign, and in the denominator there's a plus or minus sign. So then what ends up happening is you have to make very careful, you have to memorize all these different cases of when you use a plus here, when you use a minus here. So it ends up, it's supposed to be a shortcut, but it ends up having you do all of this like very specific picky memorization, all in an effort to like skip just basically understanding the concept. And I am telling all of you from years of experience that it's not even worth it. It's not even worth it. And I'm also telling you from years of experience, when we get to the, and again, this is not to criticize anybody, I promise. But by the time you get to your exam problem where you're going to be tested on the Doppler effect, the problem is designed so that you have to understand the concepts, and like you couldn't even just plug into that equation if you wanted to. So it's like a warning. When I say on the homework of the Doppler effect, I'm saying ultimately all of you is going to have to learn how to understand the Doppler effect in a way that does not rely on that particular equation. You still all can get all the points on the Doppler effect. I'm well aware that I haven't explained it yet. So it's like nobody's fault. No one did anything wrong, but it's just like a warning signal that you're going to want to move past that equation. It's not going to work on the exam. When I start explaining all this, which I promise I will, then like, again, everybody can redo and back up and blah, 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 blah. And it's no one did anything wrong, but that's, so WWW means where's it coming from? Why is it true? What is this? And you kind of want to like not have that happen in the middle of an exam. Okay, I don't know if that answers. Maybe tell me privately if I answered or not. But again, I don't mean any of that is in a shaming way. There's no way you could have known. There's no way you could have known that I don't like that equation. Although, okay, but on the other hand, for exams, what you do want to know by the time you take an exam is just don't, you do want to make sure that anything you're writing down, like, right, it did, this is why we do step 3 before we do step 4. Like, don't pull things out of thin air. Like, whoever, anybody, like the whole, well, you get what I'm saying. Like if you don't recognize an equation and you just found it for a particular problem, that's probably a sign that you're not unpacking the problem sufficiently, or that there's something missing somewhere. But okay, I don't know. Just let me know if I answered that question or not, or if now like you're like running screaming and putting anthrax in my mailbox, which is not at all funny or appropriate for me to even say. Okay. Wait, did that direct chat person did that answer? I'm like worried. All right, well, I'm gonna. Okay, I think. See, if your answers are long enough, you eventually lose the questioner. All right, so what are we gonna do now? What we're gonna do now is go back to where we were last Wednesday. Okay, the last thing we were saying, last class, is that if you take a whole bunch of identical oscillators and you arrange them in a very specific way, you can describe the entire collection of oscillators with one equation. Just switching the view. And that equation is the one written at the bottom of the page right here. Sorry, I'm just arranging the view of the. Okay. When I say a phase oscillators, when I say that you have a whole bunch of oscillators that are staggered in phase in a proper way, let me be very clear again what I mean by proper. Like you might want to write this down in your notes or whatever. I'm saying the original picture that we're talking about is you have a collection of identical vertical, let's say they're vertical. You have a bunch of identical oscillators, each one of which is, let's say, arranged along the y-axis, right? Each oscillator is oscillating along an axis that we call y, and each oscillator is identical in its parameters to all the other, i.e. they all have the same spring stiffness, and they all have the same mass, and they're all free to oscillate, therefore, at the same angular frequency, omega, because omega it always depends only on parameters, like omega is square root of k over m or whatever. So you have this whole bunch of oscillators, and they're all the same. They're all going to oscillate at the same rate. But then you arrange these vertical oscillators, you arrange them along the horizontal axis, let's say. You arrange them along the x-axis, and you deliberately make them equidistant along the x-axis. Like the zeroth oscillators on the y-axis, the first oscillators on the 1 meter mark, the second oscillators on the 2nd meter mark, etc. And then, again, this is just summarizing what I think we've been saying. And then you very deliberately have them all oscillate at the same rate, but all at different phases, at different points in their cycle. So you deliberately set it up so that the 0th one has 0 phase constant. Like when you start your stopwatch, it's at the amplitude position. Whereas the first one, the one, a meter away, is not at the amplitude position. Let's say it's pi over 2 radians into its cycle already. A quarter of the cycle already passes. So it's already at the equilibrium position when this whole thing starts. And then the next one is another, let's say, pi over 2 radians into its cycle, another quarter cycle of the way into the motion, and et cetera, et cetera. So you set these things up so that they're all staggered in phase by a constant step, and they're all arranged equidistantly along the axis. So therefore, you're arranging them so that each one is at a point in its cycle that's linearly dependent on where it is in the arrangement, right? Like that's a mouthful, but that's what I'm trying to say. I'm saying if you imagine that, and in a way, all of my words are trying to say, imagine that you arrange a bunch of oscillators that are out of phase with one another in the simplest possible way, right? That's what I'm saying. I'm saying that just their phases are staggered in a manner that is directly proportional to where the oscillators are in the arrangement, right? If you do that, then the entire arrangement can be captured by this one equation, y equals a cosine omega t plus kx, where, what we said last time, we said k is this new concept. K is and I think it was Raymond who sort of put this elegantly last time in class, like k represents the constant of proportionality between the phase of any given oscillator and the location of that oscillator along the x-axis, like, right? So K is measured in radians per meter, right? Whereas, and again, I'm technically right now, I'm just like summarizing where we are so that I can do something with it and move on. But K represents a measurement of radians per meter, a ratio of radians to meter, whereas omega has been meaning radians per second, right? So omega is a constant that is adjusting or affecting the independent variable of time, whereas k is a constant, an adjustment on this other independent variable of space, right? So now in the end of the day, if you ask the question, what is the height of a given oscillator in this arrangement? The height, what is y, the dependent variable? If you say, like, how high is an oscillator in this whole arrangement, this whole horizontal arrangement of vertical oscillators? If you say, I want to know the height of an oscillator, what we're now saying is, well, that height of an oscillator is now a function of two independent contributions, two independent inputs. If you want to know how high an oscillator is, on the one hand, you have to specify when you're looking, like at what moment in time are you looking? Because everything is like shifting all the time. But also you have to specify where are you looking? Like at any given moment of time, this oscillator's here, this oscillator's there, this oscillator's there. So if you want to know height of oscillator, you have to specify what time you're looking and where you're looking. If you specify both of those, then we could say, oh, the oscillator, the fifth oscillator that you're looking at over at the fifth meter, oh, at the 39th second, oh, that oscillator's right here at this height, right? We now have a function of two independent variables. And that's that function right at the bottom. First time ever in this class, really first time in your science or math investigation. I mean, if you're like most people, like we've never really dealt with a function of two variables before, but now we are because each oscillator was a function of time, and now we spread out all these oscillators in space, right? And so both are operating. Okay, let me be very specific about this. I mean, I know in a way you know this. This is a big punchline. In a way, this is the punch. In a way, what I'm about to say is the whole purpose of Lab 3, except backwards. Like what I'm saying is, and stop me if this is not clear. Anyway, stop me if it's not clear. But you set up a bunch of oscillators that are each oscillating vertically. Like every one of these objects is moving up and down, purely along a y-axis, right? But you stagger them in phase, and then you let this thing go. So it's like up, so it's like, like this. Now, if you stand back and watch what's happening, or in your mind's eye, you stand back and watch what's happening, what I think becomes apparent is that what you'll see is what we would describe or what we'd identify as a wave motion or a wave pulse. You see a wave. What I'm arguing is that one way to make a wave is to make a vast collection of phase-staggered oscillators. And in effect, that's what you are trying to see directly in Lab 4. But what does that mean? What does it mean to say that we've made a wave? Well, first of all, it means we've made an unthingy thing for the first time. We have made some kind of immaterial motion. What do I mean by that? I'm saying if you stand back and look in your mind's eye at what you would get if you put together these springs going up and down in this way, what you eventually see is something moving across the x-axis. What you'll see either something that we're going to call a pulse. What do I mean by a pulse? Well, what do I mean by a pulse? Um, okay. What a pull? Oh, can I go back? Yes, absolutely. Sorry. Yeah. Okay. Um, and let me know when. Okay. Wait, and let me know when. Got it. Okay. Thank you. Awesome. That's points right there too. Okay. What I'm trying to say is this. I mean, and these are like definition. I mean, these are triple equal signs, what I'm saying. I mean, they're English, but I'm trying to say that if you stand back and observe a wave pulse go across this collection of oscillators, what it is that you're observing, what you're noticing, what you're seeing is that something like a crest, right? Or a trough, like a bump, like a hill, or a valley, like flows across the x-axis if you do all this right. And if you and that's what you recognize as a wave. You're like, oh, look at the wave going across. Just like if you're standing at Coney Island and you see like a bump of water coming in towards you, you're like, oh, here comes a wave. But think about what you're saying when you recognize that. I mean, we can all recognize it. We're all aware of this concept of wave, but what is it that we're recognizing? What's going on? What we're recognizing is a shape. Really, in fact, what we're recognizing is a misshape, like a contortion or a distortion, or what we would call or a disturbance or a perturbance. We're noticing that something is out of shape, and we're recognizing that out of shapeness, and we're tracking it with our eyes as it goes across. In other words, when you see a crest travel from left to right across this bunch of vertical oscillators, right? What your mind is saying is, wait a second, if everything were still, if everything were just normal, the masses were all just sitting there, it would just be a flat line of oscillators. If the oscillators were at equilibrium, the shape that we would expect that all the oscillators would form together would be one long horizontal line, right? But they're all vibrating around and everything. So now we start seeing distortions from equilibrium. We start recognizing shapes like, oh, there's a hill over there. Oh, there's a valley over there. And when we say that something is moving or flowing across, what we're noticing is, oh, that hill over there that I noticed, maybe I'm even calling in my mind hill number one or crest number one or whatever. I'm noticing as that hill sort of flows its way along the x-axis. Like that's what's moving, right? Is a shape that is distinct from what the normal equilibrium shape would be. So we're saying, oh, a shape is moving across, and we call that like wave motion. And that's all true. I'm not saying anything's wrong with that, but that's very interesting. Because if you agree with me, or and please tell me if you don't, or if if you understand what I'm saying, and please tell me if you don't. What that means is that what's moving is not a thing, right? I mean, there's no actual hill. There is no object that is shaped like a hill. The only object here are a bunch of little masses on springs. There is a bunch of material particles that together we call the medium. The medium is the collection of material particles, each of which is oscillating in its own individual zone. And the net effect of the whole thing is to see that some sort of shape, some sort of arrangement of the material particles becomes recognizable to our eye, and then it flows across, and then it flows in along an axis that no individual particle is ever moving along, right? In other words, what I'm saying is this. Like what's weird is I'm saying in English, every one of these particles is only moving along the y-axis. There is no particle that is moving along the x-axis. Yet we see something move across the x-axis. And it's not an illusion. Like we don't just think we see it. Like we can track it. We can measure. We could say, oh, the wave is over here now at position 1. And we can start a stopwatch, say 5 seconds later, it's over here at position 9, 9 meters. We could say, oh, it moved 8 meters in 4 seconds or whatever. Oh, so it has a velocity of 2 meters per second. And then we could predict, okay, if it keeps going at this velocity, which it will, we'll know, we'll be able to predict how much time it's going to take before it's 6 more meters, farther across the room. In other words, we can track with our eye this bump or this valley, and we can do physics to the bump or the valley that we're tracing with our eye. We can measure a velocity. We can predict a final position. We can do all of our physics equations to it as though it were a thing, but it's not a thing. It's not a thing. It's a shape of things, right? In other words, what I'm saying is, I want to just make as concrete as possible. This is English. I'm trying to be intuitive here. And then we're going to be mathematical next. But I'm saying when you recognize wave motion, you say, oh, it's a wave. What you're really saying is that you're seeing something flow from here to there but there's no individual thing that flowed or traveled at all from here to there. That's what you're saying. In other words, it is unthingy. You're set wave motion. Whenever we recognize it, I'm not saying it's not real. In fact, I'm saying it's very real. But I'm saying whenever we recognize wave motion, we're recognizing a very real kind of motion that is not material motion. We are saying when we say a wave moves from left to right, we're saying there is motion going from left to right of something that we can measure, we can reproduce, and we can predict. So it's like totally subject to science, like a motion that is scientifically, physically real. It occupies space and time in that scientific way, measurable, reproducible, and predictable, right? So when we see wave motion going from left to right, from point A to point B, we're observing and measuring and reproducing and predicting a motion that in fact exists and takes place from point A to point B, but for which no individual material, countable, identifiable, separatable, massive, tangible particle ever makes the trip from A to B. Something goes from A to B, but it's not matter. It's not a particle. That's what wave motion is. Okay, that right. So it's to me, it's fascinating. It's really the purpose of this course. Like all the math that we've been doing up until now, I've been trying to we're trying to put together the mathematics and analysis that we need to understand like how ultimately immaterial motion occurs in the world. And what I'm saying right now is ultimately how immaterial, the first way that you can have an immaterial motion, something moving from there to there that is not a thing, is what you have to have is a bunch of things all harmonically oscillating in a very particular way, the particular way that we set up yesterday and that we described with this equation that I'm about to analyze. The collection of the material particles then becomes called, so I'm saying you need to have material particles to do this, but they all do something very specific, so specific. So it's like a bunch of material particles oscillating in such a well-arranged dance in time and space that then something emerges, this new motion. So a bunch of these particles are each only moving vertically, but then this motion comes out that is horizontal, and it's a motion of something that is not a thing. Like right now, I'm calling it a wave. It is a wave. So the vast collection of particles that you need for this to happen is called a medium. The identifiable shape or disturbance in the medium that you track as it flows from one place to another, we call a wave pulse. So the pulse is the disturbance in the medium, the disturbance from equilibrium of the medium shape. And when that disturbance flows from one place to another, we call that propagation. Propagate. The word propagate, where to go? Yeah, down here at the bottom. The word propagate means flow, or really all it means is to travel, to move, but it's the word that we always use from here on in. If someone says, oh, that thing is propagating, they're just saying it's moving, but they use the word propagate to emphasize the fact that the thing that they're talking about is not actually a thingy thing. Like, so propagate is to wave pulse as travel is to particles, if that makes sense. Like we just say propagate when we're trying to emphasize that what's moving is non-material. It's a wave pulse. So propagate means flow. Wave pulses flow through a medium. Now you need the medium for this to happen. A wave is a wiggle in time and space. But in order to have a wiggle in time and space, you need things to be wiggling. Those things are the harmonic oscillators. Together, they're called a medium. All right, so that's like my summary of. So we're into unthingy things now, and we made this unthingy thing with by making a collection of phase-staggered oscillators. It can be described by this equation, and all of that reason. So we had we've been having the equation A equals cosine omega t for a long time now. Like a lot of the midterm exam is all about just this A cosine omega t thing. That A cosine omega t by itself is a oscillator in time. But the minute you have a bunch of oscillators and you spread them out in space, you get this extra term, kx, right? And what you've created once you do that is called a wave. Hence, that's why this k thing becomes known as you know, as the angular wave number. Like, notice the other one is called angular frequency, right? This is just called angular frequency. You can have this. You need this just to have an oscillator. This is just called angular frequency. Just to have one oscillator oscillating in time, it will do so at a certain rate. We call that rate angular frequency. But once we have a bunch of them and they're not only oscillating in time, but also in space, then the whole thing becomes a wave. So we call that K the wave number. Like you don't have a wave unless you have the K piece. Okay. So this is now wave motion. So now, looking at the time, so we have, okay, 25 minutes. So let's consider deeply this setup. So now I'm saying this is a collection of phase staggered oscillators. That's one way to make a wave. Again, lab 4, that's what you were doing explicitly. Lab 3, you were looking at this in reverse. You were like making a wave, looking at the wave, and ultimately understanding by making the graphs and everything that what a wave is cosinusoidal harmonic oscillations in time and space at the same time. Like you were breaking apart a wave into its time and space pieces in lab 3, and then you were putting them together in lab 4. Hopefully by the end you see that what we're saying a wave is harmonic oscillations in time and space at the same time. So I want to consider more deeply this equation. No, this equation now is, as we mentioned, a function of two independent variables. It's a multivariate function. Y is the output, the inputs are x and t. So if I want to do what I always do in physics. I want to take some derivatives. I want to particularly take two derivatives. That's what I'm always interested in physics. Like I'm always interested in acceleration of some kind or second derivative because F net equals ma, right? But here, if I want to take some derivatives, I'm going to have to use that piece of knowledge, the one piece of knowledge that I gave you very quickly last class. Like if you want to take derivatives of a multivariate function, you have to take partial derivatives. So I'm going to take some derivatives. I'm going to take two derivatives. I'm going to take a total of 4 derivatives. I'm going to take two partial derivatives. Well, yeah. I'm going to take two partial derivatives of this equation with respect to time, which means treating space as a constant. And then I'm going to take two with respect to space, treating time as a constant, right? So I'm just going to do it. So I'll write the equation again. I mean, the function. And every time I'm writing plus, I could be writing minus. It's plus or minus, really. Plus or minus, but so first we're going to take the first partial derivative of y with respect to time. Now, no, I'm using those new symbols now that we said last Wednesday. It's a partial derivative. It means rate of change of y with respect to time holding x constant, right? That's what it means. And should I say this? This is exactly what you physically did in the lab 3. Like when you made graphs, like first thing you did was at one point, you picked a particular x value, right? This is when you clicked on that button in lab 3 when it said um, um, allow multiple frames per something, allow multiple frames per image or something like that. When you picked a certain X, wait, I'm getting myself too bogged down. Just in lab 3, after you took a movie of the wave pulses that you set back and forth along the strings, you took a movie of that. And then in one case, you picked a certain X value, you held X constant, and you just watched as the spring went up and down when a piece of metal went up and down some y-axis or some ruler that you had fixed at some position x, right? So you had a reference line like a ruler, and you watched as the metal intersected that ruler at various heights, and you put red dots there, and then you from the red dots you made a graph, right? And you allowed that to happen. You allowed multiple frames per you allowed multiple dots per frame. That's it, I think. Multiple points per frame. So what you were doing was you were picking a particular X, you were holding X constant, and you were letting time flow and seeing how Y changed with respect to time for a given horizontal position. Right? That's what you were doing when you made one of the graphs in lab 3, whether you understood it that way or not at the time. So you were in effect you were taking a partial derivative with respect to time, i.e. holding x constant, right? And then you did the other thing. Then you stood back and you unclicked the allow multiple points per frame, and you just made a bunch of red dots across the whole thing. In other words, you looked at a snapshot, one frame. I guess this was the anyway, you understand what I'm trying to say. This is when the box was unchecked, actually. But the other option was you picked one moment in time. You held t constant for one value, and you asked how y was varying with respect to x. Your two different graphs were just isolating the dependence on two different independent variables, that one at a time, treating them independently, right? And that's what we're doing here mathematically. If we take the partial derivative of y with respect to t, it means take the derivative of this function, but treat x as a constant. Treat x as a constant. We're not saying it actually is. We're saying pick one and hold it in our minds so that we can observe or examine the t dependence. So to do that, we would take the derivative according to our usual rules of trigonometric derivatives and chain rule and all that. So we get negative a omega sine of omega t plus or minus kx, right? Notice what happened when I took one derivative with respect to time. When I do the chain rule, I'm saying the derivative of the inner piece, the derivative of the parenthesis, is just omega. Like omega comes out because omega is multiplying time, which I'm treating as the variable. K, you might think would come out because it's multiplying a variable, but I'm treating that variable x as constant when I take this partial derivative. So if x is a constant, then a constant times a constant is just a constant, and the derivative of a constant is 0, right? So the partial derivative of y with respect to t is negative a omega sine omega t plus kx. And then if I take a derivative again, the second partial derivative of y with respect to t. This was all the analysis that you were doing of lab 3 that, again, you might not have known what was going on then, but now hopefully you're still hopefully this is now making some sense. So I take the derivative again. So omega comes out again from chain rule, but sine turns to cosine, and the negative sign doesn't change. So I get negative a omega squared cosine omega t plus or minus k x. So that's the second partial derivative with respect to time. So what? So put that in my mind over here for a moment. And now look at space. So that's like going to, now it's like unclicking the allow multiple images per, allow multiple points per frame or whatever. So I go to space. Whoops, sorry. If I go to space, now x I'm treating as the variable and I'm holding t as a constant. So what comes out of chain rule this time is the k, not the omega. So I get negative a k sine omega t plus or minus k x. And then if I, right, the k comes out, the omega does not, because now t is being treated as a constant. So then I do it again to take the second derivative, because I always care about second derivatives in physics. And I get negative a k squared cosine omega t plus kx. Like the whole thing in the parentheses keeps going along for the ride. Okay, so now what? So what? So now I've got a statement about an expression for the second partial time derivative, and I've got a statement for the second partial space derivative. I want to relate them to, I want to see how they're related to each other. And they seem very related to each other because they both have that cosine, like that, they're both end in that cosine term that's identical. So what I'm going to do is rearrange both of them. I'm going to rewrite each of these. I mean, this, what I'm looking at is, I'm looking at this, and I'm looking at this, and I'm going to rearrange each. Oh, sorry. I'm going to rearrange each. You can't, I don't know if you can see that. Like this is identical in each one. So I'm going to divide each one by like negative a omega squared or negative a k squared to get the cosine term by itself. So this one, all right. So this one, I'm just rewriting it. The time derivative, okay. I'm just dividing both sides by a omega squared so I can get the cosine term by itself, right? And I'm going to do the same thing with the other one. Similarly, now, why did I do that? Because if they're each equal to that cosine thing is identical. They're both those pieces, the time piece and the space piece are each equal to that identical cosine. So I can set them equal to each other, right? I mean, they are equal to each other if they're both equal to cosine. So I'm going to say, so set equal to each other, set equals, whatever, set equal to each other. Right. And so they're set equal to each other. Now the negative a's cancel out from both sides. So what we have left at the bottom is omega squared and k squared. So I'm going to multiply both sides by omega squared and multiply both sides by k squared. Well, I'm going to multiply both sides by omega squared. I'm just going to multiply both sides by omega squared so I can get one derivative by itself. I get this. sorry. Or in other words, this. Now this, I know I've written it on the front of the board like a number of times in the last couple of weeks, but this is a huge deal. What this is, okay, what this is in the center of the page is, first of all, it's the second differential equation that we've seen in this class so far. We saw one, now this is number two. The first differential equation we saw was the differential equation for simple harmonic oscillation. That someone's entering that I don't think is in this class, but okay. I'm gonna wait. Like let's get this clear. We've seen one differential equation already. That's the differential equation for simple harmonic oscillation. I'm going to write that again in a moment so you can compare and contrast. But this one, our second differential equation, is the differential equation for waves. They're very similar, but they are different. Any motion that ever satisfies this equation, any solution to this equation describes wave motion. Anything that is a wave or anything that looks like a wave or acts like a wave must be describable by this differential equation. This is ultimately the rigorous mathematical definition of what it means to be wave motion. Wave motion means that at every single point in space and every single point in time, we are satisfying this relationship. Now, it's a pretty thick looking relationship. Like, what is the relationship saying? And by the way, it's called the one-dimensional. It may seem weird that it's called the one-dimensional wave equation. I mean, there's actually two dimensions of space involved and a dimension of time, right? But what we're saying is this equation is what's used to describe wave pulses that are flowing, propagating back and forth along one dimension of space, i.e., these waves are going back and forth along the x-axis, right? As opposed to ripples on the surface of a pond, which are going all not just back and forth, but like all over a plane. That would be a two-dimensional wave. Or ultimately, there are other kind of waves like that actually exist in three dimensions of space called light, which are three-dimensional waves. But so this is a one-dimensional wave, like ripples on your stretched slinky spring is what we're describing here. Isn't it? Hold on. There's someone in the. I know it's 7 minutes. I'm just checking. Someone in the waiting room. I'm not sure. I reckon. One second. One second. What happened to? Hold on. 1 second. Oh, I see. Okay. Okay. Now, most of your exam is about the differential equation for simple harmonic oscillation. And simple harmonic oscillators are not waves. Waves require simple harmonic oscillator, but a simple harmonic oscillator, a mass going back and forth on a spring, is not a wave. Put together a whole bunch of them in space, then you have a wave. A wave is not just something that's oscillating in time. It's something that's oscillating in time and space, right? So let's compare. Like the differential equation for simple harmonic oscillation looks like this. Now, very similar, but different. Okay, first of all, so you might want to write this down. I know we're running out of time. You might want to take, like I'm saying, we have two differential equations in this class so far. First is simple harmonic oscillation. Second is waves. Let's go side by side. On the left side first. Very, very similar. The left sides are almost identical. It's just that one, for simple harmonic oscillation, happens to be a regular ordinary derivative. The one for waves is a partial derivative. Why is that? Because for a simple harmonic oscillator, an oscillator is just a function of one variable, time, whereas a wave is a function of two variables, time and space, right? That's difference one. But other than that, the left side is the same. What they're both tracking on the left side is acceleration. Like what the simple harmonic oscillation equation says. Oh, no problem. Got it. Direct type. I just didn't recognize the first. Got it. Direct type person. Thank you. Okay. And we have 4 minutes left. Okay. Let's look at the Hooke's law, like the harmonic oscillation. Like what does that equation mean? It's saying, remember, and this you really want to understand for the midterm. What the first equation is saying is that the rate at which or say a vertical oscillator, if I'm making it vertical, the rate at which the oscillator accelerates back to equilibrium, right? The left side is acceleration, second derivative of position with respect to time. So the left side is saying the rate at which an oscillator accelerates back to equilibrium is what? Look at the right side, is directly proportional to how far away it is from equilibrium. Like that's what that y is, right? The y is displacement from equilibrium. So Hooke's law, the whole point of elasticity of an oscillator is if you want to, in other words, if you're at equilibrium, you don't accelerate at all. You have zero acceleration. You're where you want to be. Even if you're moving, you're not accelerating. The farther away you're stretched away from equilibrium, the harder, the faster you accelerate back to equilibrium, right? So for an oscillator, acceleration of any individual point is directly proportional to displacement from equilibrium. Now, the wave equation is very similar, but it takes a left turn. The wave equation on the left side is also acceleration. So picture a wave, picture any snapshot of what you did in lab 3. Picture some point somewhere in the medium, any piece of metal, right? At any given moment, that metal is accelerating back to equilibrium, just like a mass on a spring. It's accelerating back to equilibrium. And it's accelerating at a rate that is directly proportional to something. I say directly proportional because again, I don't have a negative sign this time. That's a slight difference, but in parentheses, I have some kind of constant, omega again, over the new constant, the space constant. So now space is being taken into account, but it's still a constant, omega over k, right? So the left side, acceleration is directly proportional to something. What's the something? Now it's no longer y on the right side. It's second derivative of y with respect to x. I know we have 1 more minute. Second derivative of y with respect to x. Hold on. Didn't we already say second derivative on the left side? Like, is this circular? Are we going back? Like, didn't we already? Well, no, we didn't, because this is now second derivative of y with respect to space, not to time. So this term right here, this is the key difference. And we have 1 minute, but let me say this. This is second derivative with respect to space. In a math class, if this were a pure math class and you just had a graph of y as a function of x, first derivative of the graph of the picture is slope. Second derivative in a math class, derivative of derivative in a regular everyday math calculus class, y is a function of x. No time, not physics, just y space, x space. First derivative measures slope of the graph. Second derivative measures concavity. So what are we saying here? What a wave is a situation where the rate, you pick any piece of metal at any given time. I know it's 4:20. I'm going to finish the sentence and we're done. At any given moment, at any given place, a piece of metal will accelerate back to equilibrium at a rate that's directly proportional to the concavity of the metal at that point, i.e., what does concavity mean? It means like how much like a bowl is it? How curvy curved is it? How not flat is it? So we're saying the rate at which a piece of wave medium goes back to the medium's equilibrium, the rate at which it goes back is not dependent on how far away it is. It's dependent on how bent, how deformed, how disturbed the medium is at that point. A wave is a traveling disturbance. So this is like the concept of restoring force, or like the concept of Hooke's law, but being blown up, not only from time, but into space. I'll say it one last time, and this is it. I'm saying Hooke's law oscillation is the rate at which you accelerate back home depends on how far away you are from home. In a wave, the rate at which you accelerate back to flatness depends on how bent away from flatness you are at that point. It's not dependent on displacement, it's dependent on concavity. That's what the wave equation says. And the constant of proportionality, omega over k, we'll discuss next period. Okay, you've been very patient. It's 4:21. Again, I will hang out for any questions or anything, but I'm going to turn off the recording and you can go and have a nice night. And there's no new homework. We're all just catching up and learning, blah, blah, blah. So thank you. And yes, thank you. Thank you. Take care. Okay, I'm going to stop, not myself, but the recording.